here we have this interesting setup of a drone and a bonfire. And this is supposed to be some new technology where you have the drone that grabs some water and puts off the bonfire. And as you can see here with the very accurate drawings, very detailed also, we have a good visualization of the situation. So the drone is L1 away from the river. The bonfire is L2 away from the river. The distance between the drone and the bonfire along the river is L. And what else? And the drone will go to point X. So it plans to go to point X and then grab some water, then go back to put off the bonfire. And here this type of word problem is about making the right interpretations. So if you can set this up in this very nice visualization, very accurate as well, and then you can solve the problem. But if you cannot, then you cannot. So this is very important. And now, assuming that you're able to do this, then what do you do next? Well, I want you to focus on this fact. So x minimizes the travel distance, which means we have a function for the travel distance. Maybe I'll call it d. And this function we need to minimize. But first off, we need to write it down. And since I've already used brown for the distances, then maybe I'll use brown again. What is the distance function? Try to pause the video and think about this for a moment. But simply, this is a right angle triangle. And so the first distance, this first distance here, this first arrow, is equal to the square root of L1 squared plus x squared. If you've ever heard of the Pythagorean theorem, of course. That's the first arrow. And the second one is, it's this distance. You know what this distance is going to be? Yes, it's L minus this x part. We have L minus x squared plus L2 squared. Okay, so we have a function in terms of x. Why is it a function in terms of x? Why is it not a function in terms of x, L1 and L2? Well, because they are constants. The distance between the drone and the bonfire is fixed in this problem. But what we can change is the point at which the drone goes to the river to get the water. Because if we find the best point at which we can do so, then it will be great, because it would take us less time to put off the bonfire, and then maybe it would save lives. So this is very important matter, in fact. Okay, then to minimize, you need to find x such that d prime of x is equal to 0 as a start. Let's find the derivative of this function. So this will be the lower arrow prime plus the upper arrow prime. Derivative of the lower arrow is don't ask me how I know this. It's an extra formula you can use if you have. This is not part of the course, but I'll maybe write it here for the sake of enrichment. So it's f prime of x divided by 2 square root of x. So that's how you differentiate square roots. You usually use the, what's it called? The power rule with replacing the square root with the power of half. But just use this directly, then there's no need for that. That is a note on the side, and then if I want to take the derivative of the upper arrow, is this one, so by this I mean that part, then it's the same thing. In the end, the denominators won't matter because we want to set this to be equal to 0. And so only the numerators will matter in that case. More or less. This is perhaps not the most accurate statement to say. But okay, so you get this is 2 and this is the derivative of this is what the expansion is L squared 2xl plus x squared. And this is a constant, so its derivative is 0. This is a constant, so its derivative is 0. And this is minus 2l, and then this is 2x. Since taking the derivative is not really the focus of this very specific exercise, I am not giving it too much attention. So I'm cancelling stuff out. Just cancelled out the 2's together. And now since I have the derivative, I can write it down as follows. And then you would like to set this to be equal to 0. And then I would like to take a moment. Yes, I see it now. So it's very important to take a break whenever you feel that you're stuck. So here, if this is equal to 0, then I can just add this term to both sides. And if I add it, I get x minus L. So I get the opposite of L minus x. Yeah. But then notice that this is a square, right? So I can just write it as L minus x. And then this is very nice, because I want you to notice this very specific detail. Maybe I will use black. So x and x squared. Then we have x minus L. Okay, maybe I should... x minus L. Then you have x minus L squared. And then you have L2 and L1. So you could say that x is equal to x minus L whenever L1 is equal to L2. Because it's like you're just placing the same things. Now this is of course between quotations, and it takes a little bit of focus to notice it. You can of course always try to explicitly solve the equation But if we want to make this mathematically precise, we say that there is a ratio that's preserved. So x is equal to x minus L, that is true, whenever what? Whenever the denominator, which is, let's say, L1, is equal to L2. And then in that case, we get that L1 divided by x is equal to L2 divided by x minus L. Yeah, just a small typo. It's L minus x, it's not x minus L. We had something that looked like this. So when we add both sides this term, we get that this is the positive part and this is the negative part. And I have replaced everything back in place accordingly. So L minus x, L minus x, L minus x. So be careful when you add things to both sides. This is very important.